Hey everybody, this is Larry. This is day 23 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about House Robber 3. The new place again. Okay, so this is the other House Robbers, I suppose. And okay, so no, you don't rob adjacent houses. Okay, so this is again going to be dynamic programming. And there are a couple of ways to formulate it. The way that I'm going to formulate it is just by recursion and by top-down memorization. And yeah, so I'm going to write it the kind of the way that I generally write it. Not in context because I wanted to make it more explanatory. So definitely let me know what you think about that. But the idea is the same thing that or similar thing to if you have solved House Robber 1 or House Robber 2. And I definitely recommend you try 1 and 2 first before solving this if you're having trouble with this. I think getting that intuition and visualization then allows you to kind of understand this one a little bit better. And I probably have videos on it. You could search on YouTube. I could maybe link below or something like that. But yeah, okay. So basically, we could define this recursively, right? The key thing to make an observation about is what does it mean to rob a house, right? So let's have a recursive function. Let's write the most naive recursive function for now. Well, maybe not the most naive, but a slightly naive recursion formulation of it. But yeah, so basically, let's just say you have a max money robbing this house, right? So I would also say I'm going to write this in a way that is maybe not the way that I would write it during the contest again. I mentioned this. I would probably write this in a cleaner, or not cleaner, just like a more shorter way. But I want to, the way that I'm writing this right now is to help you learn and visualize. So definitely let me know what you think. So basically, so I could break it down to two functions, right? And let's start with the root. We could either, well, two things, right? Rob this house or don't rob this house. So let's break that down. So let's go. How do I name? I'm just trying to think about a name that is clear for explanation. But yeah, let's just say max money can rob house maybe. So we get given a node, right? And that means that this is the max money that we can get while we can rob this current house, right? So we have two constraints, which is whether we can rob this current house or not. And then we have another function maybe to help us while it's max money cannot rob house, right? So these are kind of my templates for now. And yeah, so let's kind of think about how they relate to each other, right? So maximum money can rob house. What does that mean? So, well, if node is none, we just return 0. I mean, I think this is straightforward. You have no more houses, right? So there are two things you can do. You can rob this house, so you can either rob it or you don't rob it, right? So what happens when you rob this house? Well, when you rob this house, that means that, let's say you start the root. When you rob this house, it means that you cannot rob the children, right? So, okay. So is there a way to express that? Well, we actually have a helper function that we cannot rob house, so we can definitely use that. So now we're trying to express, okay, how do we calculate this, right? So let's just call it money, say. Maybe I'll rename it, is equal to, well, if we rob this house, we get no dot value plus the max money, well, that we cannot rob house of no dot left plus max money cannot rob house no dot right? Why is this the case? Okay, so basically this is the money you get from robbing the house. This is the I talk so much about robbing the house that I'm afraid that like the FBI will kind of come knock on my doors. But yeah, but plus you cannot rob the next house. So you cannot rob the house to the left and you cannot rob the house to the right? But you want to get the max, function to go about, right? So this is money robbing house. It's a little bit, you know, but yeah. So then now, what about money not robbing this house, right? Well, if you don't rob this house, what does it mean, right? Well, this function is 0 because, well, you don't get any value for this house. Plus, max money can rob house because you can now rob the house to the left and the house to the right. Oops, typo. Right, and then now given these two functions, and obviously I write in a way that, like, add 0. I know that adding 0 doesn't change anything, but I just want to be explicit. Now we just have to return the max of these two numbers, right? Money robbing house, and then money not robbing house. Okay. And then here, in the same way, now we have to implement, well, before I do that, let me just say that the way that I write this, even though it is not the way that I would write it, in a contest because for speed purposes, it's still the way that I would think about the problem. And I like to write code that is very close to my Dart, because when you debug it, it makes you ask a question of, is this really what I want to say, right? Just a thing. So this Dart process is actually very close to how I would think during a contest or during an interview, but it might not be, maybe I would use shorter variable names, for example, but okay. Anyway, so now let's implement this function, right? So clearly, if you cannot rob, if there's no house, it's going to return 0. And then now you cannot rob this house, so you can only not rob this house, right? So now money not robbing house is equal to, well, 0 for the same reason as before. And then max money can rob house, no dot left, plus max money can rob house, no to the right. So this is exactly the same function as here. And once you do enough of these problems, you can definitely, I will max back. Well, you have no choice, so you can only make this decision. So that's what I'm going to return. And once you do enough of these type of problems with memorization and dynamic programming and so forth, you're able to kind of see, well, okay, we can actually combine it into one function or something like that. I'm not going to do that for this video, but just know that, yes, you're not, you could definitely make this shorter. You could definitely make this, but I just want to make sure that we all understand how these functions work, right? And then now we just have to go back to the first house to kick it off. And we just have to go return the max of, well, the only two decisions we get to make to kick it off in the beginning. Actually, yeah. Well, no, I mean, there's no, there are two decisions, but the state is that in the beginning, you can rob the top house, right? So just return max money can rob house of node, of root. And that's pretty much it. I'm going to add in, so this is the naive recursion algorithm, or naive-ish recursion algorithm. We're going to go over memorization next, if you're struggling with dynamic programming or whatever. But this is basically the recurrence. This is how you relate to each other. And I'm going to, just want to, at least the examples to kind of show you. And hopefully it's right. And the ends are small enough that you're not going to run into issues. As we kind of get, they don't give you the constraints, but as you get more and more, you can prove this for a reason that it's going to give you a timeout error, right? And I can kind of, I can just generate a big array to show you that, right? So that's what I'm going to do. This is just a random big array. I don't know what the answer is, but that's okay. I think this should time out. I didn't really count how many elements there is. Okay, well, actually, apparently it's still fast enough. So let's make this even bigger. That'd be funny if you didn't need dynamic programming on this one. But eventually, you're going to get to the point where, wow. Did I memorize for no reason? By accident? Okay. Well, I don't know how many ends this is, but I would still say that, especially given that you don't know the end, you're definitely going to run into some timeout issue at some point. Okay, well, I mean, it is getting slower, but okay, my point is still that maybe not quite yet. Maybe because it's a full tree or something. I don't know, but still, as n gets bigger, you notice that this gets, this takes 1 second, which is something to benchmark against. It's a rough benchmark, but if we have 10 of these cases, it's gonna be too slow, so we're gonna get time limited, right? So okay, so how do you solve this time limited issue? Even though I have trouble showing it. Well, we do something called memorization, right? Well, notice that for each node here, we might make the same. For the root, you're going to call it once, but for other nodes, you may repeat. You may repeat cores, meaning that the same core may, happen all the time, and the same input will always give you the same output, right? So the idea behind this memorization is that because the same input will always give you the same output, let's just save it down so that I even think about it as caching in a way, in that you just save down the results so that you can fetch it later, right? And for this, I'm going to use a dictionary. So let's just call it cache can rob house. So let's just make this a dictionary. If node is none, that's fine. If node is in if node in can rob house, then we would just return return this thing, right? So we return from the cache if it's in the cache. Otherwise, we at the very end we set this up to be this thing, and then we just return it from the cache as well, right? And similarly, we should do this the same way, but I just want to see quickly if that made a huge difference to timing. Hopefully it does, otherwise then it's a little bit weird. See, but yeah, immediately it went down a dramatic amount, right? From 1 second to 68 millisecond. And you could, which is kind of ridiculously good in performance. We should probably do it to the other one just in case. But I think this one is actually relatively less code, but that's okay. And during a contest or an interview, I wouldn't, risk needing to prove that this is true. So yeah, so let's cache it again, and we'll go over the complexity analysis afterwards, which is going to be really soon. And again, this may look familiar because not here, because we just did it on the other function, so it's really similar for that reason. Okay, and now when you run the code, bam, another dramatic pivot. I mean, it's small enough that you might not notice, and maybe it's just random fluctuations, but you can definitely see it from 1 second going to 48 millisecond, right? So that is why we do something called memorization, because we put these we put the answer in a memo so that we don't have to need to get it later. Okay, so what is the complexity of this, right? Well, we start by looking at each function. Okay, how many possible inputs are there to this function, right? Well, for each node, for each different node of the tree, you're gonna call this function once, or so you're only going to call it for each node of the tree. So that means that it's going to be O of n number of nodes, right? Or n nodes precisely, actually. N nodes, and each one of these will do O of 1 work, if you will, because this does O of 1 because this function does O of 1. This function does O of 1, so all this does O of 1 work. So then what is the complexity of this? Total complexity is just n node times O of 1 work, which is O of n total complexity for time. In terms of space, you can also show that it is linear, because for each node, there's only one entry for each node in the cache, right? So that's going to be linear. In the same way, you could show that this is linear as well, both time and space. So yeah, that's all I have for this problem. Let me know what you think. Hit the like button, hit the subscribe button, join me on Discord. Let me know if you have any questions, because I really do want to, be able to explain this in a good way if you're not understanding it. So anyway, I will see y'all next problem. Bye-bye.